Okay, the semi-stable reduction theorem.
Distracted by it.
Okay, so today's the title in the schedule was the growth and monogamy theorem. So this is not that. The reason I'm giving a slightly different talk is, so a couple of years ago, Ramon gave a talk about the growth and monogamy theorem, and has very nice, clearly typed notes on his website. So at some point today, I will mention the growth and monogamy theorem, but I will not give the proof because that's given in Ramon's talk. So what I'll do instead is essentially an application of the monogamy theorem, which is to proving the semistable reduction theorem. So I'll explain what the semistable reduction theorem is and talk about how it relates to the monogamy theorem around these terms. Okay, so just to recall briefly the definition. So if A is algebraically closed, so then proper connected curve C over K is semi-stable if all non-smooth points are these ordinary double points. So étal locally they look like. So I guess in this so every point that's étal locally like this, because this also has a smooth point, so that's fine. And we also have the notion of, so if we have G over K group scheme, let's say smooth commutative is semi-abelian, if there exists an exact sequence, say exact sequence of what's, let's go into that in a sec. Okay, so what are these things? So this is my G, and this is an abelian variety of K, and this is a torus Gm to the R for some R. Notice I'm working over an algebraically closed field, so every torus is, in general, a torus is something which is a twist of this, but because we're working over an algebraically closed field, let's just assume it is this. Okay, finally I should say, what does the exact sequence mean? Exact sequence, say, of FPPF sheaves or smooth sheaves or étal sheaves. Okay, so, you know, this thing is surjective on, as a map of, say, étal sheaves. So if I have a morphism from T to this thing, then T emits an étal cover which relates to this thing, the usual kind of thing.
But okay. You can say it in an elementary way, no? I mean, G to A is
smooth surjective. And
smooth and surjective, yeah, and
yes.
The kernel is this.
Good point. So equivalently, F is smooth surjective, and T is the kernel of F, i.e., which is by definition G cross A, the unit section of A, or where EA is just the origin of A. Okay. Fun exercise, check that these things actually have the same meaning. Wonderful. So last week Eric gave us a very nice talk. So what did Eric do? Well, Eric did many things, but there's a small part that I want to expect, which is that if C is semi-stable, then fix 0 C over K is semi-abelian. And so actually Eric told us rather more. He told us exactly what the A is, namely it's the sort of pick 0 of the normalization, or if you like the product of the pick 0s of the product of the Jacobians of the components of the normalization of C. And T, or at least the rank of T, is given by H1 and the graph we attach to C. We have two ways of attaching a graph to C, and you should pick the correct one, and this will be true. This is the one which has a loop in. Okay. And actually this is an if and only if, which was not covered in Eric's talk, which I will not explain more about now. There's maybe a nice place to read about this is algebraic groups and class fields. There's also there's an English translation. This is the English translation. There's of course the original French version. which has a Frenchified name. If you speak French, you should read the French one because it'll be clearer, but if you don't speak French very well, okay, we should be a little bit careful here. This is a well-known thing, there's sort of a warning. So C smooth implies X0C is abelian, but the converse fails. And the classic example is two copies of P1, one glued together at a point. There's my C, it's clearly not a smooth curve, but pick 0 of this thing is just a point because every line manual here is, well, every line manual of degree 0 here is trivial. So, okay, so somehow semi-stable is better than smooth because for semi-stable we have this if and only if. For smooth we don't have the if and only if. This is basically the only thing that can go wrong with this converse direction, so it's rather harmless. But one has to be a little bit careful. Okay, so the next thing I want to do is I want to state the semi-stable reduction theorem, which is sort of the main.
Is the converse true if the genus of C is non-zero?
No. For example.
Oh, then you get there.
So basically, take any smooth curve and glue on a rational tail, or take any two smooth curves.
Glue two
smooth curves pointed together transversely to the point. And then, so if this is, say, C1 and this is C2, so if this is my C, then pick 0 of C is just pick 0 C1 times pick 0 of C2, all over K, omitting K. So in particular, if these are both abelian, then this is abelian. Well, actually, if and only if. So. And of course, there's nothing special about two of them. You could join any number of them, as long as you join them in a tree. So the intersection should be transverse, and it should remain a tree, because as we know, the rank of the toric, so the rank of the toric part is given by the h1 of the graph, and we've already said that these things are automatically semi-stable because by this theorem. So in fact, pick 0 is abelian if and only if C is semi-stable and the graph is a tree. But again, be careful which graph because you can find two. So pick the one with loops, or pick the one that might have loops and check that it doesn't have loops. Okay, any other questions about this so far? Everybody's happy? Wonderful. So the semi-stable reduction theorem, let's head for a statement first. So S is going to be regular Noetherian connected dimension 1. I wonder if I can drop Noetherian from this if it's still equivalent, but it doesn't matter. Let's not worry about it. K is a fraction field of S. So this is a Dedekind scheme. So the regular and the dimension 1 are certainly very important, otherwise the whole theory falls to, well, certainly gets very different, as we'll see later on. The connected equivalent irreducible is just to make sure that this has a meaning. If you want to generalize beyond this case, this is merely a sort of technicality, and you can easily extend beyond this case at the expense of the phrasing becoming slightly more complicated. Okay, so let's suppose we have C over K, a smooth proper curve. Say geometrically connected. So it has semi-stable reduction. If there exists a model that is a semi-stable model. So what is this thing? So this is a proper flat C over S, such that all of the geometric fibers are semi-stable curves in this sense. The only slight subtlety is the exists. It's perfectly possible that there can exist a non-semi-stable model, and that there will always exist a non-semi-stable model. Take a semi-stable model and blow it up in some non-smooth point and blow it up in a stupid way. So to prove something doesn't have semi-stable reduction, it's not enough to demonstrate a non-semi-stable model, but blah, blah, blah. There's a nice sort of the handy thing is that it has a semi-stable model if and only if the minimal regular model is semi-stable. So if you want to check whether something, I mean this needs some proof, but it's not so hard. So if you want to check whether something has semistable reduction, if you want to prove it doesn't have semistable reduction, the most natural thing is to write down the minimal regular model and observe that that thing is not semistable. Okay, so, great. So suppose we also have A over K as an abelian scheme. Well, you can kind of guess what's coming next. It has semi-abelian reduction if there exists a semi-abelian model.
The K should be a capital K.
Oh, thank you very much. There is no little K at the moment. Well, there was one over there. Yeah, indeed. So A over K is an abelian scheme. It has semistable reduction if there exists a semi-abelian model. In other words, we want a smooth commutative group scheme, sort of which is a model of this, over S as a model of this thing, and the fibers should be semi-abelian varieties in this sense, the geometric fibers. Okay, again, we have to say there exists. It's possible you could make some silly model, and you shouldn't do that. So we can also ask about uniqueness. So certainly a semi-stable model is not unique. Supposing I have something like this. Supposing I even take a smooth model, and then I blow up a point here, then I'll introduce the extra copy of P1 in the fiber. So this thing is not unique, but it's fairly clear that this resulting surface is not minimal because I could always contract the P1 again, and it turns out good. So we have, if you want a unique thing here, you should take the minimal regular model. You can also ask about uniqueness here, but here we are saved by a result of Raynaud, which tells us that if there's a semi-abelian model, then it is unique. That only requires that S be normal and can be of any dimension, and then if a semi-abelian model exists, then it is unique. So this is very nice. The reference, finding a reference to this is kind of confusing. It almost appears circular at some point, but if you dig around, then you will find the result.
But also, if S is just a Dedekind scheme, is it still hard to find a reference?
I think the thing is that people always refer to, it's just like, I mean, you follow the pointer to Raynaud's thesis or something, and then when you read the result of Raynaud's thesis, it doesn't actually look like the theorem you want, but then you have to think a little bit, and then you realize that it does imply what you want. But it may well be that there's a standard result for, so I don't know, there may well be a cleaner reference for over a one-dimensional base.
Maybe the linear Mumford, they use it, right?
Oh, maybe you're right.
For the evaluative criterion.
But where I've seen it, so I haven't checked the bit of linear Mumford recently, but whenever I see this result stated, it's always just reference Raynaud's thesis.
What is the result?
The result is that if S is, say, a Dedekind scheme, then any two semi-abelian models of the same thing are canonically isomorphic. It is in Raynaud's thesis a bit varied.
I think you have also, it should be an SGA3 also, no?
Oh, maybe.
Yeah.
Okay.
I mean, you have so many torsion points that
yeah, is this in the case of a Dedekind?
well, no, in general, on any base, I think.
But it's false, because you have to have a normal, otherwise it's false. There is some subtlety. I mean, so you can use Wouter, your thesis gives a counterexample that is in the normal case, I think, after some thinking.
It's about torsos.
No, that's not what you use.
No, but I thought you could play around with your thesis. But anyway, maybe I misremember. So.
Are you playing around with my feet? It's like,
Oh no,
it's not really written down.
Okay, it's clear that if you have a if you take a non-normal thing, then you can group things into different ways.
Yeah. Yes.
So that is true. Yeah.
Yeah. And so. Yeah.
Yeah.
Okay. Oh, so there's another point. The other thing I was supposed to say here, when we're talking about uniqueness, is if we have an abelian scheme over the generic point Dedekind scheme, we already have a nice model due to, for example, Peter's thought, well, due to, I guess, the work of Raynaud and Néron, namely that A also has a Néron model. Also, A has a Néron model, which we could call N over S. Now, this Néron model is in general not going to be a semi-abelian scheme. Even if A has semi-abelian reduction, this will not be a semi-abelian scheme because the fibers of this thing will generally not be connected. So let's introduce the notation N0 for the connected component of identity. sorry for the small writing, I'll just move up here. So if I have any smooth scheme over some base scheme S, and a section of this smooth scheme, then this section has a sort of an associated fiber-wise connected component, and basically what it is, it's some open subset of my scheme, such that on every fiber it is actually just the connected component of my given section. So we have to let's draw an example. If this is my S and this is my how do I draw? This is a terrible picture, I'm sorry. Okay, so here my fiber is connected, and here my fiber is connected, but here my fiber has two connected components. So if here is the unit section, then to take the connected component of the unit section, well, the whole scheme is connected, so this doesn't make any sense. But what I want to do is I want to take the fiber-wise connected component, which I guess looks like this. And now we see the terribleness of my drawing. Because apparently this is open. It's not a good picture, I'm sorry.
You can have a connect degenerating in a union of two lines, right?
Yes.
That's two dimension. And then you just remove the intersection point of the two lines, and then you have your non-connected fiber.
Yes. So let's take like xy equals t or something.
So inside P2, a family of conics.
And here's my A1 with coordinate t. So at some point I get these two components. Or these are my conics. And then over t equals 0, I have two components.
So it's in the affine space now. A2 over KT.
But how do I draw?
Well, they should intersect and you remove the intersection.
Yeah.
Yeah.
Your intersection is at infinity now, so
Yeah,
it's fine. It's good. It's exactly right.
Oh yeah, it's true.
You want that, but
Yeah,
you shouldn't say it's in P2.
Yeah, I should.
It's in A2.
Yeah, but now it's, but now the thing is everything. I mean, the connected component is exactly what you drew.
No, there is in
Okay.
fiber over T is 0. You have two components. So,
And they meet at the point of infinity.
so you see that.
Which I've deleted.
Okay.
So indeed, so here the connected component of identity, this is the connected component of identity is the complement of
That thing.
that thing. Not sure if this picture is actually better than that.
It is.
It is, okay.
It's an interesting thing.
But this has an equation, and this was just some hand waving.
Yeah,
So yes, it is certainly better.
This is precise. You,
Yes.
you have, you could write the equation x times y equals t.
Yep. And so this is, the conic, but I removed the point at infinity, so the singular point at infinity. Actually, the whole section at infinity, which doesn't make any difference to us. Okay. So this was a thing. I hope I haven't just made things more confusing, but somehow when I was learning these things at first, people would always talk about the connected component of identity of an elliptic curve, and I'd be like, what? It's connected? That doesn't make any sense. But it's this notion of fiber-wise connected component of identity is what people generally mean. Okay. And so the point of that was to say that A has semi-abelian reduction if and only if N0 is semi-abelian. I'm sorry, again, I'm not going to talk about how to prove this because I can't actually remember, but I just wanted to sort of mention this as a remark. If you're, again, if you're given some abelian scheme, you find yourself a non-semi-abelian model and you want to know that has semi-abelian reduction, then you can compute the narrow model and that will tell you whether or not there could be a semi-abelian model that you're missing somehow. Okay, so let's take the theorem 3.6. So of SGA 7 part 1, x plus a x. Okay, so I should have said this at the beginning. So this is the reference I'm using for this whole talk. SGA 7.1 x plus a 9, which is actually surprisingly readable. It surprised me how beautiful it was. I started at the beginning and it all made sense. It was very nice. So here is three. So when I give numbers to theorems and propositions, the numbers are from SGO. Yeah, the only thing which was unpleasant about reading this is the horrible quality of the scan that I have. Okay. So S Dedekind, which already been capitalized, and K is prime. Now I'm doing the thing where I write out all the assumptions again because it's the main theorem. So then there exists K prime over K, finite Galois, field extension, such that a K prime, the base change, has semi-abelian reduction over what? S prime, which is the normalization of S in K prime. Now there's something which is obviously weird about this theorem, which is that I've only defined what it means to have semi-abelian reduction over a Dedekind scheme, and it's not a priori obvious that this S prime is a Dedekind scheme, but it turns out that it is, and this is the Krull by the Krull-Akizuki theorem. So this is Dedekind by Krull-Akizuki.
Well, it is a Galois extension, right? So you have a separable extension. I think you get it for free. If it is inseparable, then maybe you need something. But for separable extensions, you have a trace form. You have you can show that the ring of integers is finite over the ring of integers down. It's regular. It's normal by definition. It's Noetherian because it's finite. So what can be wrong?
Ah, okay. Okay, so right, the step I was missing was the finiteness from the. But okay, if it's a separate extension, then it should be.
But there you use that it is Galois separable.
Yeah, and then
it is true in the inseparable case, but
then
it's harder.
Yeah, okay.
Yeah.
Okay, so this theorem is unnecessary. Okay, thank you very much. This is good to know. So we can make this slightly easier. Okay, so this is the semi-stable reduction theorem for abelian varieties. You can tell because it says A over K is abelian. There's a natural analog for if I replace A over K by C over K, a curve, smooth over curve, then, well, the statement of the theorem makes sense and it remains true. And this is the semi-stable reduction theorem for curves. Oh, maybe I won't erase that just yet. So, let me for a moment, what should I write? C okay. So this is a corollary. It's the same theorem with A over K replaced by a curve smooth over C over K. Of course, and then replacing semi-abelian by semi-stable. Otherwise everything goes pretty fine. Why is this a corollary? So proof of the corollary, apply this 3.6 to Jacobian of C. And then by this theorem, by this statement only, we make some extensions such that the Jacobian requires semi-abelian reduction. Well, there's something to be said. Because this is only a statement of fiber by fiber, but it works out fine. Okay. Yeah, let's trigger. Yeah, I'm triggering something under the carpet here. You need to know that this pick 0 is the identity component of the normal model. But Peter established that in his talk, so we're okay. So I'm cheating slightly. But you can. I mean, this can be turned very quickly and easily into a proof. Okay, so I'm writing the curve version as a corollary of the abelian variety version. Actually, these are actually equivalent. Well, they're both true, therefore they're formally equivalent. But there's an easy way to go either way. So we've just sort of sketched how to go from here to here. If you want to go from here to here, what you do is you say, well, take my abelian scheme, and then I'm going to write it as a quotient of a Jacobian, which I can do. So I take my abelian scheme and I slice it by some hyperplanes. And then if I do this enough times, generically enough, Bertini tells me I'll get a smooth curve out of it. And then if you stare at the, is it Lefschetz hyperplane theorem? That tells me that somehow some map on pi1s is surjective, which tells me that I end up with a surjection from the Jacobian of the curve to my abelian variety. And then you need to know that if I have a quotient of a semi-abelian variety, that is again a semi-abelian variety, which is a result of Riemann. So actually, if you prove this thing, then it implies this thing. So you can choose which one you'd like to prove. And people have given direct proofs of both of these things. Generally, to prove this in a direct way, one does by playing around with models of my curve. So I start with some model of the curve over S, and then I start blowing it up, and then I make little field extensions, and I blow it up some more, and possibly I assume that S is excellent at some point, otherwise I get stuck. And so this is sort of, you can prove this in a sort of very hands-on and explicit way.
Which not so much in the case where you need Wild ramification, I think. Right? That is if you want to do it with models of the curve, then it's hard to see which extension you need.
Yes.
As long as if a tame extension will suffice, it is very easy. But if you need Wild, then which Wild extension exactly is necessary?
But people do give direct proofs of this thing.
Yeah, but then they do it without knowing what to do.
Right.
They do it by giving upper bounds on possible graphs.
Ah, yes, okay.
It's very unpleasant business, I think.
Okay. So this right-hand approach, the approach to proving the right-hand side directly is more direct if you're lucky, but if you're in some horrible case, if you need Wild ramification, it gets very complicated, so maybe you don't even gain so much. On the other hand, the left-hand side we can prove in a very sort of clean, direct way. Should I pause soon for the video thing?
It's just a little
button. Okay. I could do like. Okay. So I want to do a couple of sort of application motivation things, and then maybe we can have a pause, and I'll start to talk about the proof. So, only very briefly, but the theorem, the semistable reduction theorem, is clearly a theorem about things of a Dedekind scheme. And so, what if you have an abelian scheme which is not over a Dedekind scheme? You might think, well, this does not help me at all. But actually, this has some very nice applications. Are they whispering to me? I don't think so. I'll just carry on. I'll assume everything is fine. So, some applications